June 2023 Physics Regents exam. In this video, we're going to be covering part B2, which is 15 short response questions, each worth 1 point. A link to this test can be found in the description of the video below if you want to follow along at home. That being said, we're going to start off with 51, which asks us to determine the potential difference across the battery. So whenever we want to find a potential difference, we're going to be solving for the voltage. And it's very important for us to figure out what type of circuit this is, because certain circuits have different formulas for voltage. Don't believe me? Check your reference table, right? In a series circuit, the voltage is equal to, the total voltage of the cell is going to equal to the sum of all of the different voltages across the cell. Whereas in a parallel circuit, the voltage is always constant, okay? So in this case, we need to figure out whether this is a series circuit or a parallel circuit. This is going to be a parallel circuit because our resistors are arranged parallel to one another. If I were to draw this circuit out, I would have one resistor that's over here and another resistor that's over here. These are part of two parallel lines. These two wires that they're attached to are parallel to one another, right? They don't touch. If this was a series circuit, the resistors would come in a series, right? One after the other. So it would go, here would be your first resistor, here would be your second resistor, and here would be your third resistor, right? They come in a series, 1, 2, and 3, okay? That's obviously not the case here. They're parallel to one another. So because this is a parallel circuit, we know that the voltage is going to be the same across the entire circuit. V1 is going to equal to V2, which is going to equal to V3. So no matter where you put this voltmeter, it's always going to read 12. It's going to read 12 volts here, 12 volts here, 12 volts here. Anywhere you put it, it's going to be 12 volts. So if we go into our answer booklet, this is where you're going to put all your answers to the short response section. We'll put 12 volts and we get full points. Okay. 52 asks us to determine the current going through the 6 ohm resistor. So again, this is another important reason to determine whether this is a series or a parallel circuit, because in a parallel circuit, the current is not the same. In a series circuit, the current is the same. So that's another key difference. So we have to calculate the current, which is going to be different across both resistors. And we're going to calculate it across the 6 ohm resistor, okay? So I'm going to use the equation R equals V over I. It's in your reference table. It gives you the resistance based on the voltage and the current. So I know that my resistance is 6 ohms, right? This resistor is rated 6 ohms, and that's going to equal to my voltage, which is 12 volts, divided by an unknown current. So I have to ask myself, 6 ohms is equal to 12 volts divided by what? Well, 6 ohms is going to equal to 12 volts divided by 2 amps. So the answer is 2 amps. Always remember R equals V over I and plug in the values that you know. So in our answer sheet, we're going to put 2A. 53 to 54 asks us to calculate the equivalent resistance, which is the Req, of the circuit, and to show all work, including an equation and substitution with units. So in this case, if we look at our reference table, we see that Req represents the equivalent resistance, and that in a parallel circuit, that's going to equal to 1 divided by the Req, and that's going to equal to the sum of 1 divided by all of the resistors. So in order to get full points, I need to write down the equation I'm going to use to solve this problem. So I'm going to write down 1 over Req is equal to the sum of all of my resistors divided by 1. So 1 over R1 plus 1 over R2. Now the reference table says 1 over R1 plus 1 over R2 plus 1 over R3, so on and so forth. I stop at R2 because I only have 2 resistors in this circuit. Okay, then I just need to do substitution with units. All that means is you just plug in whatever values you're trying to solve for. So 1 over Req is what I'm trying to solve for. I don't plug anything into that because I haven't solved for it yet. And I plug in whatever's left. So whatever's left is this 1 over R1. So the first resistor I knew was 3 ohms. And plus the second resistor, which I knew was 6 ohms. So here's my equation, here's my formula, here's my substitution with units, and now I can just skip to my answer, and my equivalent resistance is going to be 2 ohms. Okay, how did I do that? Well, all I did was I just combined this, right? I know that 1 over Req is going to equal to 2 over 6 plus 1 over 6, right? You have to convert the 1/3 into 2/6, right? Because whenever you want to add fractions, you need to find the lowest common denominator. If you combine that, that's going to equal to 3 over 6. So 1 over Req is equal to 3 over 6. If this part confuses you, you can just flip this. You can flip 1 over Req into Req over 1. so long as you flip this other fraction as well. So you can flip that into 6 over 3. You'll get that Req over 1 is equal to 6 over 3 because you just flip these two fractions, which is equal to 2 ohms, okay? You don't need to show this work here, but if you're confused on how to do that, there it is. So the next question says that the diagram below shows parallel straight wave fronts approaching a rigid barrier that has a small opening in its center. On the diagram in your answer booklet, draw at least 3 wave fronts after they have passed through the opening, okay? So here we have these waves, and they're passing through a slight opening. And in order to get full points, you need to remember diffraction, right? As waves pass through small openings, they tend to bend around that opening, right? Almost like a Wi-Fi signal, right? This is how your Wi-Fi can reach all parts of your home, even though it's in a different part of your house, right? Let's say, you live in a 1-floor home and the Wi-Fi router is in the corner of this room, and you're using the computer in this corner of the room. If waves were stopped by barriers and couldn't pass through them, the Wi-Fi would never reach to you. But as the Wi-Fi goes out from the router, it hits these barriers, these walls, and it passes through these doors and other cracks in your home, and it kind of spreads out, right? It diffracts outwards, and it gets to cover the entire house because that's just a fundamental property of waves. So in order for us to get full points here, we just need to draw 3 diffracted waves, or 3 waves that curve outwards from the hole that they put there, right? This hole. So in our answer sheet, that's exactly what we're going to do, okay? So we're just going to draw 3 waves that look something like that, okay? Just make sure that your waves have the same wavelength, right? So the distance between this point and the distance between this point and this point should be the same value as distance between this point and this point. So I would take my ruler out, I would measure the distance between these 2 wavefronts. Let's say that's equal to 1 centimeter. And when I draw my next wavefronts, I want to make sure that I draw them 1 centimeter out from one another. So I would just measure out 1 centimeter on my ruler, put a mark, put a mark, put a mark, and then just connect them with this curved line. That way they're all the same distance. Because whenever something diffracts, the wavelength or the distance between the 2 crests, which is the wavelength, is going to be the same, right? It doesn't change. So 56 through 57 is going to rely on this situation up here. It says that a projectile is launched from ground level with an initial vertical speed of 26 meters per second upwards and an initial horizontal speed of 15 meters per second. Neglect friction. Calculate the total time the projectile is in the air before it returns to the ground level, okay? So in this situation, let's say that this is our ground level, and let's say that this blue dot is my projectile. Right, the second that it's launched, the projectile is going to go up by a speed of 26 meters per second, and it's going to go across or to the right by a speed of 15 meters per second, okay? Now, obviously, it can't go up and to the right. It can't go to the right and then magically go up. This ball is going to, or this projectile is going to form some sort of arc, right? It's going to go up, travel up, and then it's going to hit the ground down, right? So we want to calculate the total amount of time that this took, the total amount of air time, the time from when it was launched all the way until it hit the ground again, okay? So for this, you need to know this is a projectile motion question. So for this, you need to know a very key principle, right? You need to know that at the top, right here, the Vy, the vertical velocity, is equal to 0 meters per second, and that the time that it takes for the vertical velocity to reset or turn to 0 meters per second is equal to the time it takes for it to reach the ground. So this time is equal to this time. And if you add those 2 times together, you get the total amount of air time, okay? And this makes sense because as the ball is going up, it's decelerating, right? Gravity, which is going to be 9.81 meters per second squared, is accelerating this ball downwards, right? So every second that the ball is going upwards, it's losing 9.81 meters per second of speed until it reaches 0. And then its velocity, 0 minus 9.81, is equal to negative 9.81. So then its velocity turns negative, which means it goes in the opposite direction. So instead of going up, it then goes down. So all I need to do is I need to calculate the amount of time that it took for this projectile to lose all of its vertical speed and then just double that time. So one of the best formulas to use for this is going to be that Vf, where the final velocity is equal to the initial velocity plus a times t, okay? So in my answer sheet, that's the formula I'm going to use. I'm going to say that VF is equal to VI plus A times T. And then I'm going to substitute with units. So I'm going to say that 26 meters per second is equal to, not 26, I'm going to say that 0 meters per second, which is my final time, my final velocity, that's the velocity when it's at the top of its path, is equal to my initial velocity, which is 26 meters per second, minus 9.81 meters per second squared times t, which is what I'm trying to solve for. Okay? The reason why it's negative 9.81 meters per second is because the acceleration is in the opposite direction to the travel, right? The ball is traveling upwards, but gravity is accelerating it back downwards to the ground, right? That's why it's slowing down. So that's why it's negative. Anytime something is opposite, it's usually negative in physics. So now all we have to do is solve for t, and you know that t is going to have to equal to 2.65 seconds. But we're trying to solve for the total amount of time. So now we need to use the second equation. Like I said here, the amount of time it took for the ball to reach the peak, right, and reach 0 meters per second is equivalent to the amount of time it takes from the ball to reach the ground, right? So that means that my t total is equal to 2 times the t up, 2 times the amount of time that it took for the ball to reach that peak. So now I know that my t total is equal to 2.65 seconds times 2, and that my t total is equal to 5.3 seconds. So that's going to be my answer here. Okay, number 58 is going to ask us to determine the total horizontal distance that the projectile travels before it returns to the ground. So we just calculated the amount of time that has to happen in order for the ball to go up and then down. Now this ball isn't just being launched directly into the air. It's not just going up and then down in the same position. It's being launched forwards as well. So as this ball is increasing altitude and decreasing altitude, it's also moving towards the right at 15 meters per second. So every single second that passes, the ball is going to move 15 meters. And well, if the ball traveled for 5.3 seconds, then, and every single one of those seconds it travels 15 meters, that means that you just multiply those two values, and you get that the ball traveled 79.5 meters during that ascent, right, or during its path. Finally, the last problem for this little group of problems is 59, and asks us to determine the angle above the horizontal at which the projectile is launched. So again, we can just draw our setup here. So let's say that our ball is in the red, and at the time that it's launched with an upward velocity of 26 meters per second and a horizontal velocity of 15 meters per second. And like I said, it's going to follow this path upwards, right? It's not just going to have an upwards velocity and a rightwards velocity. Its velocity is going to be mixed, right? It's a mix between these two velocities, right? So it's asking us what angle was it launched at, right? What is this angle relative to the ground? The way we solve this is we have to play around with our vectors, right? So always with a projectile motion question that asks you to calculate the angle at which something was launched, you usually write down the vector diagram, right? These are all the vectors. These are the different speeds that it's launched at, and you just need to rewrite this vertical component over here. So if I rewrite this vertical vector, this 26 meters per second over here, look what I can form. And if I extend the object's path just a little, the projectile's path just a little bit longer, I now form a right triangle. And whenever I have a right triangle, I can use my trig functions. I can use SO, CA, and TOA, right? So you know that sine is equal to opposite over hypotenuse. You know that cosine is equal to adjacent over hypotenuse, and that tangent is equal to opposite over adjacent. So the tangent of this angle is equal to 26 meters per second divided by 15 meters per second. Okay, so we need to solve for this magic angle that when you plug it into tan, it's equal to 26 over 15. So whenever you're solving for the angle, you're going to use the tangent inverse function on your calculator, because the tangent inverse of tan theta is going to just give you the angle. Okay, and we're solving for the angle, so we want the angle alone. But whatever I do to one side of the equation, I do to the other side. So I need to find the tangent inverse of 26 divided by 15, and that's going to come out to approximately 60 degrees. Okay, so in our answer sheet, you're going to go ahead and you're going to bubble in, not bubble in, but write 60 degrees down. That's the angle at which it was launched, okay? So always remember that whenever you're dealing with these type of problems where you're trying to calculate some sort of angle, always write down these steps, right? Always write down what's happening. Even if it's in terms of meters per second or speed, always write it as a vector. So number 60 is asking us to use a ruler and to determine the scale used in the diagram. So here we know that a 20 Newton force is acting due east on point P, and a 25 Newton force due south is acting concurrently at point P. So at the same time, there's a 25 Newton force acting south, which is in somewhere in this direction. Okay, and it's a scale. It's drawn to scale representing a 20 Newton force, and we need to find the scale that's used in the diagram. So whenever something is to scale, there's some sort of formula or some sort of conversion that's used in order to plot it out there, right? There's some sort of thing or some sort of conversion that correlates the distance on the page to the amount of newtons that it represents. In this case, that correlation is going to be to 1 centimeter. So 1 centimeter on this page is going to equal to some sort of newtons in this world, right? So unfortunately, I don't have access to a ruler on this program that I'm using to explain this, but if I did, and if I was taking this test, I would put a ruler starting at point P, and I would measure all the way to the tip of this arrow. And what I would find is that this tip corresponds to 4 centimeters. So that means that 4 centimeters in real life corresponds to 20 newtons on the diagram. Now I want to solve for 1 centimeter, what 1 centimeter is equal to. It's equal to blank newtons. So I can divide both sides by 4, and I get that 1 centimeter is equal to 5 newtons. Okay? So that's all you have to do to determine scale factor. You measure it out to the unit that they want it to, and then you convert it to one of that unit. Okay? So 61 says, on the diagram in your answer booklet, use a metric ruler, so again, using that centimeter, and the scale shown in the diagram to draw a vector to represent a 25 Newton force due south acting at point P. And it asks us to begin the vector at point P and label its magnitude in newtons. So I need to label its magnitude, so I need to label that it's 25 newtons, and I need to have the right direction. So when I want to construct this vector, I'm going to follow my scale. I know that 1 centimeter is equal to 5 newtons, so 25 newtons has to equal to how many centimeters? Well, how do I go from 5 to 25? Well, I multiply by 5. How do I go from 1 to x? Well, I multiply 1 times 5 to get 5 centimeters. So 5 centimeters is equal to 25 newtons. So in order to correctly represent 25 newtons, I need to measure out on my ruler 5 centimeters and then draw a straight line that's going down. Why down? Because it said it's acting due south. So I'm going to draw one. Make sure that your arrow ends right at the 5 centimeter mark of your ruler, and make sure that it's a straight line, okay? So if you were to, draw this line and then remeasure it with your ruler, this tip, the tip of this arrow, should match up with the 5 centimeter mark, okay? And the last step you need to do is you need to label this as the 25 Newton force, okay? So as long as you have the arrow that's facing downwards, it's labeled, the scale is correct and direction is correct. They even included a compass for you. You're going to be all set for this problem, okay? So 62 asks us to determine the magnitude of the resultant force acting on point P. So again, this is one of those problems where it's like the point P can't go to the right or down at the same time, right? These two vectors are this force is going to be combined in some sort of direction that's a mix of both of them, okay? I did not mean to erase that vector, but again, it's not like this vector can pull point P down and then pull it to the right by 20 newtons. They're acting concurrently, which means they're acting at the same time. So whenever two forces are acting concurrently, there's going to be a combination. In reality, the force is going to be a combination between these two other forces, right? In this case, it's going to be a force that's still going down, but going down to the right. So it's going to look something like this, right? There's going to be a resultant force that's somewhere in this direction. So what the Regents wants you to do is calculate that resultant force. The way that I want to calculate it is by using another trig function, So I know that I have a easterly force of 20 newtons. I know I have a southerly force of 25 newtons, and I know that my resultant force is going to be somewhere between here. So again, I can do my magic where I just rewrite one of these vectors on the opposite side to form a right triangle. So once I form my right triangle, I can just solve for the hypotenuse, which is my resultant force. So you need to know that a squared plus b squared is equal to c squared. So this is c, this is a, this is b. They're just the two legs of the triangle. So I know that my 20 Newton force is one of my legs, plus my 25 Newton force, which is another leg, is equal to this resultant force squared. So this is going to equal to 1025. And if you take the square root of both sides, you're going to get that it's equal to 32 newtons. So C is equal to 32 newtons if you solve that in your calculator, okay? So this is going to be 32N. So another way you could have done this is by constructing a resultant vector and then using your scale factor to convert. So you could have constructed the vector by moving this one down. I did not mean to do that again. You could have drawn two construction lines like so and like so, connected this to this end, and then measured that. But again, I think a more surefire way of doing this is just by doing it using a right triangle like I just showed you. So 63 asks us to determine the amount of energy in electron volts that must be absorbed by hydrogen to excite the atom from an n equals 1 energy level directly to an n equals 4 energy level. So in order for this, we need our reference table, and we need to scroll to the energy level diagrams. It's asking us about a hydrogen atom, so we're going to go and look at the hydrogen table, and you can see that at the ground state, this hydrogen is not excited, right? The energy that it has is negative 13.6 electron volts. Now, as you excite this, as you add more energy into this hydrogen, it begins to change energy levels, right? The higher the energy level, the more energy that hydrogen is going to store. So you can see that in order for us to jump from n equals 1 to n equals 2, for us to go up an energy level, we needed to go from negative 13.6 to negative 3.4, which means that I gained energy, right? I have to literally add to negative 13.6, 10.2 electron volts need to be introduced into the system in order for me to increase that energy level. So in this case, all I need to do is I need to see, well, how much energy do I have to add in order to make it jump up from n equals 1 to n equals 4? Make sure that you have the right energy level that you're solving for, right? N equals 4 is not this line. It's actually going to be this line up here, which corresponds to negative 0.85. So I need to figure out, if I start off with negative 16.4, wait, was it? It was negative, sorry, I got the value wrong. Ground state is negative 13.6. So if I start off with negative 13.6 electron volts, right? And then I end up with 0.85 electron volts, how much did I have to add? If you plug this into your calculator, you're going to get a value of 12.75 electron volts, which means that if I had to introduce energy into this hydrogen, I would have to add 12.75 electron volts, because 12.75 plus negative 13.6 is going to equal to negative 0.85, which is the amount of energy it has at that level. Okay, so again, all I need to do to get full points, just write 12.75 down. Okay, 64 asks us to determine the sign and magnitude of the net charge in coulombs of a particle that has a quark composition of bottom, bottom, bottom. Right, so particles are made up of made up of these subparts called quarks. So whenever we have quarks, we have to look at our particles of the standard model, right? All particles are made up of either quarks or leptons. Either they're made up of quarks or they are leptons, sorry. So in this case, we have a particle that's made up of all bottom quarks. So each one of these quarks has a symbol, right, which is the second value. They have a name, which is the first value, and they have a charge, which is the third value. So here we're looking for something that's made up of BBB, which is the bottom quark because it has the symbol B, and its charge is negative 1/3 of an elementary charge. Now, when you have BBB, you have three of these. So you have negative 1/3 E plus negative 1/3 E plus negative 1/3 e. Okay, and if I want to look at the net charge, the total charge, I'm going to have to add all of this up. Remember, if you're finding the total, you're going to have to be adding. You're adding all of the parts that make up this particle. So negative 1/3 e plus negative 1/3 e plus negative 1/3 e is just going to equal to negative 1 e, or just negative e. Now, if you look here, our answer sheet isn't in e. It's not asking you for the units in electron volts. It's asking, or elementary charges. It's asking you for the charge in coulombs, right? So I need to convert from negative 1e into c. And here it tells you that one elementary charge, or 1e, is equal to 1.6 times 10 to the power of negative 19. So negative e is going to equal to negative 1.6 times 10 to the power of 19. So we have negative 1.6 times 10 to the power of 19 coulombs. That's what this is going to equal to, right? And finally, 65 asks us what type of electromagnetic radiation would contain photons each having an energy of 2.65 times 10 to the power of negative 20 joules, right? So here we're relating energy, and we're converting it either to wavelength or frequency. Why? Because whenever I want to classify electromagnetic radiation, I look at my electromagnetic spectrum, right? And this is all electromagnetic radiation that occurs or exists at different parts of frequency or different values of wavelengths, right? So it gives you a range of wavelengths and frequencies that correspond to different parts of electromagnetic radiation. So I want to convert this energy into either frequency or wavelength so that I can go back into this chart and see what wavelength corresponds to what part of this chart, okay? So if I look at my physics reference table once more, I can see that the formula I want to use is that the energy of a photon, or the energy of that wave, of that electromagnetic radiation, is going to equal to the h, which is Planck's constant, times its frequency, right? So my energy, 2.65 times 10 to the power of negative 20 joules, it's going to equal to Planck's constant, which is 6.622 times 10 to the power of negative 34. If you don't know that, it's on your reference table in the given values. Over here it says Planck's constant, it's going to be 6.63 times 10 to the power of negative 34. 6.63 times 10 to the power of negative 24 times this magic frequency, right? So if I divide both sides by 6.63 times 10 to the power of negative 34, I'm going to get a frequency that falls within the range of infrared light. My frequency, its exponent, is going to be between 10 to the power of negative 6 and 10 to the power of negative 4, not negative 3, right? It's going to exclusively, when I'm talking about frequency, it's not going to be this upper value, it's going to be this bottom value, right? That's the wavelength. If you solve for the wavelength, you check up here. I solve for the frequency, so I know my frequency is going to fall between this range right here, right? If you were to plug that into your calculator. So because the frequency falls there, you know that wavelength has to be infrared light, okay? So in our answer sheet, I can either write IR for infrared radiation, or I can write infrared light. And that's all you need to do to get full points on part B2 on this exam. If you have any questions, please let me know in the comments below. If you have any suggestions for the future videos that you'd like for me to go over, or future tests that you want me to, or topics you want me to review, please let me know in the comments below. Other than that, I hope you guys learned something, and I hope you have a nice day.